Let's jump right into this explainer. We are going to explore the absolutely fascinating physical limitations of our current AI hardware and discover how the physics of light is about to completely rewrite the rules of data centers. Look, if you've been following AI scaling at all, you know we are hitting a massive physical barrier. Today, we're going to visualize exactly how we break through it.
What's truly terrifying about the current trajectory is the massive, ever-widening gap between how fast an AI brain thinks and how incredibly slowly its neural pathways can actually feed it information. I mean, while AI compute performance is literally tripling every 2 years, our interconnect bandwidth is just crawling along beneath it. That massive expanding void between them, that's what we call the bandwidth wall. And it proves, without a doubt, that our main bottleneck is no longer the brain itself, it's the pathways.
Here is exactly how we'll break this complex engineering challenge down today. 1. AI's looming bandwidth wall. 2. The physical limits of copper. 3. Co-packaged optics. 4. Untethering AI memory. And finally 5. The optical AI future.
Okay, starting with part 1, AI's looming bandwidth wall.
This transition represents a total paradigm shift. Right now, on one side, we are totally bogged down in the familiar, messy, tightly packed world of traditional copper wiring. But to escape this current data bottleneck, the entire tech industry is being forced to abandon those physical metal traces. We have to cross over into the incredibly clean, parallel realm of light-speed optical pathways. There's just no other way.
Let's move to part 2, the physical limits of copper.
The root of this entire crisis really comes down to microscopic precision. Imagine, if you will, trying to shove a massive 10-lane superhighway through a single tiny toll booth. In hardware, this is known as the shoreline limit. To feed a modern GPU, engineers literally have to cram 2,048 distinct data lines into a physical edge that is strictly 1 millimeter long. We simply run out of physical space to pack input and output pins on the perimeter of a silicon chip.
And that physical crunch creates a multi-layered crisis. Following an electrical signal's path, step 1 is attenuation. As electricity travels, the waveform physically degrades. It basically flattens out into useless noise. Because of that, step 2 hits the power wall. We have to insert these active components called retimers in the middle of the path just to artificially rebuild that dying signal, which wastes enormous amounts of energy. And finally, step 3, you hit that harsh shoreline bottleneck on the receiving end.
So we tried solving this shoreline limit by stacking memory directly next to the GPU, a setup you probably know as high bandwidth memory, or HBM. But building vertically like this creates a severe new problem. We end up trapping extreme amounts of heat in the center stack, creating a literal thermal trap. Plus, because this memory is physically locked to the GPU on a silicon interposer, we've inadvertently created a capacity trap. Run out of memory? Well, your only option is to go buy another incredibly expensive GPU.
All right, section 3, co-packaged optics. Let's look at how we entirely bypass these electrical constraints.
The architectural shift here is just radical. Traditional electrical setups rely on those long, winding copper traces across green circuit boards that we're all used to seeing. But co-packaged optics, or CPO, completely changes the game. It pulls the optical engine directly inside the chip package itself. So data is converted into light almost instantly, replacing those millimeter-constrained copper wires with limitless fiber optic highways.
When you break it down, the physics of light offer absolute superiority. Instead of forcing physical electrons through heavy resistive copper, optics push massless photons through glass. This drops signal loss to near zero. And crucially, bandwidth density just explodes through something called wavelength division multiplexing. Basically, by using different color spectrums of light, we can stack vast amounts of independent data streams inside a single microscopic fiber. It entirely bypasses those stubborn pin count constraints of copper.
Now the real engineering magic happens directly beneath the GPU. By using an optical interposer, the system keeps the electrical journey to just a few millimeters. It converts the signal to light before it ever even hits the chip's outer perimeter. And to solve that heat issue we talked about, strategic thermal isolation keeps the delicate, heat-sensitive lasers completely separated from the high-power processor die, ensuring they don't degrade over time. It's brilliant.
And look, this extreme efficiency is literally a matter of survival for AI. Achieving less than 1 picojoule per bit of energy is totally non-negotiable.
Why? Because when you scale up to the massive 100 terabits per second bandwidth that future AI models require, even a tiny transmission cost of just 1 picojoule equates to 100 watts of power dedicated purely to moving data. Without adopting this optical standard, future server racks will quite literally melt down.
Moving on to Section 4, Untethering AI Memory.
Because we've solved the physical transmission problem using light, we suddenly unlock a massive shift in how data centers are designed. Architecturally, light gives us ultimate freedom. We are no longer stuck with the rigid bundle, where GPUs and memory are physically chained together. Optical fabrics allow us to completely decouple memory from the compute chip without sacrificing any bandwidth. So, rigid, clunky servers transform into fluid, independent pools of compute and memory that communicate blazingly fast.
Economically, this disaggregation is a total game changer. Take a compute-heavy task, like training a new model. The system dynamically utilizes a massive block of GPU nodes. But switch over to memory-heavy LLM inference, where those context windows are getting ridiculously huge, and the system just borrows massive capacity from the optical memory pool. It completely stops the incredibly wasteful practice of buying idle, expensive GPUs just to access the attached memory. You only use exactly what you need.
But we still have to obey the fundamental laws of physics. Light takes about 5 nanoseconds to travel 1 meter through a fiber optic cable. Therefore, a 1 meter physical separation between a GPU and a memory pool guarantees a minimum 10 nanosecond round-trip delay. That means a remote memory pool, no matter how vast or incredibly fast it is, can never completely match the raw ultra-low latency of HBM sitting mere millimeters away on the same chip. It's just the speed limit of the universe.
Finally, Section 5, the optical AI future.
So what happens when we accept that latency floor and synthesize these new optical pathways with the next generation of super-dense memory? Well, the ultimate high-density system requires these components to work in perfect synergy. By pairing massive optical bandwidth with upcoming atomic-level memory like FNAND at ferroelectric NAND, we get explosive density. FNAND utilizes a 10.5-volt memory window for hyperstability, and these ultra-low power IGZO channels that drop current leakage by an astonishing 96%. This extreme energy efficiency means we can physically stack over 1,000 layers of memory without overheating the optical layout around it.
And this brings us to our final composable ecosystem. Picture this. You have your GPU compute engine paired really tightly with ultra-fast Tier 0 HBM for instant processing. But integrated right next to it is the CPO optical interposer. Data shoots across those optical pathways to a massive, standalone Tier 1 fan-and memory pool. We have effectively engineered a limitless architecture that completely erases the traditional physical boundaries of a computer chip.
The paradigm has completely shifted. Our source research really hits the nail on the head here, noting, the question is no longer when HBM will hit its limit. The question is how much memory we can pull outside the GPU while sustaining peak AI performance. The era of electrical constraints is officially coming to a close. Leadership in AI is going to unequivocally belong to those who master the physics of light.
Which leaves us with one final, thrilling question to ponder. When we finally shatter the bandwidth wall and transition entirely to these fluid optical networks, what incredible breakthroughs will a truly unconstrained AI supercomputer bring to the world? Thank you so much for walking through this explainer with me. Keep exploring the limits of what our data infrastructure can really achieve.